class. So today we're going to be looking at chemical equilibrium. Chemical equilibrium has to do with forward and reverse reactions in a chemical reaction. We focus on one and then we're going to get into the other. So as you can see here, let's pretend this bottom arrow is not there. We start out with reactants, and as we have reactants, they will start colliding with each other to produce a product. So what will happen is that we'll start out with a lot of reactants, but as they start being produced into products, the amount of reactants goes down. However, the amount of product goes up. Now what happens on this side is that the molecules on this side will start colliding with each other, and they will start pushing back into being producing the reactants. So that will now also start forming a reverse reaction. So we have the reactants being forwarded into the product, and now we have the product being forced back into the reaction. So we have rate of a forward reaction and we have a rate of a reverse reaction. Eventually, the rate for both of these will hit chemical equilibrium, meaning, for instance, as an example, look at these ants. For every one molecule of reactant that's produced to a product, you'll have one molecule of product that's produced back into the reactant, and that never changes. So even though the concentration amounts could be completely different here, like this is here, once this chemical equilibrium locks in, those concentrations are going to stay locked in as long as the rate does not change. So for every one here, there's one on this side. So here's a couple slides that just go exactly over what I just stated. As we start, we only start with a forward reaction, but as more of the products starting to be produced, they will start colliding with each other, and eventually you'll start getting a reverse reaction going as well. And given enough time, we will have a forward and reverse reactions going on simultaneously, which will lead to a chemical equilibrium where the rate will not change unless something's been done to the system, and it will stay that way where one goes, another one goes back, and the concentrations stay whatever concentration they are. So I mentioned earlier, and let's take a look. This is all just information I jumped on from the first page. A reversible reaction occurs in both forward and reverse directions at the same time, and so you're looking at two rates. You have a rate for the forward reaction and you have a rate for the reverse reaction. Write the forward and reverse reactions for the following. So here we have an equation that is in chemical equilibrium. So you have to know which one is the forward, and you have to know which one is the reverse one. So in this case, the forward reaction is listed exactly how it's put down. We have our reactants and we have our products. And in this case, the forward reaction is showing our reactants being produced into the products. Now this is a little weird and I don't really like it, but this is how the book is showing it to you. It's asking for the reverse reaction, and all you have to do is flip it. So what it's doing here is, I would think that this would be good for the forward and reverse, since it's showing both. But Pearson doesn't want that, so we're going to follow Pearson's way, and they want to highlight on the reverse reaction. So we not only flip the arrows, but you bring the products over to where the reactant side, so you can show that this is actually highlighting the reverse reaction. I found this other slide that I felt was, it's a little kind of blurry, but it kind of gives a good explanation as to what's happening here. So we have reactants of A and B, and they're put into a beaker together. Now, as they're put in the beaker together, no products have formed. This is the beginning. This is the initial. Time has just started on it. So reaction begins, no products form. High rate of collisions, because there's a lot in there. So there's a very high forward reaction rate. Now, as it starts going, you see there's a little tiny arrow here, and that's because now we've produced some product. Not a lot of product, but some product in here. Enough of that product is coming together and colliding that's forming just a little small arrow that's showing that a small amount is going back into the reactant side. So products form, collisions between reactants decrease. Rate of forward reaction starts decreasing. Reverse reaction begins. So now, as we're starting to use more and more of the reactants, they're decreasing on this side. And this arrow that's showing the forward reaction is starting to slow down, while this one, the reverse, is starting to pick up. And in the last one, we have an equal. So what we do is we have an equal amount of reactants being produced to products, and we have an equal amount of the products being going back into reactants. And this is an equilibrium. They sometimes call it dynamic equilibrium, and the concentrations are constant. So whatever the concentrations here are, they're locked in, as well as the concentrations here are locked in. This will stay going this way forever unless something changes to the system, where one will go this way and one will go back that way. So now we can take a look at a graph here. Okay, so let's take a look. Let me read this. As the reactions progress, the rate of the forward reaction decreases and the rate of the reverse reaction increases. At equilibrium, the rates of the forward and the reverse reactions are equal. So let me explain this. This is a graph. So this is the x-axis. This is the y-axis. Now, excuse me. This is the y-axis. This is the x-axis. Now, this is a, let me take a look here. This is an energy diagram that's a plot for the rate of forward reaction and reverse reaction. So y is the reaction rate, and as the arrow goes up, it's increasing the reaction rate. And so that means what's being, the rate it's increasing. I think I already just said that. Sorry, I'm looking at my notes on here. And the dotted line and the rate, this is the progress of the reaction going. So let's take a look. Let's start with the forward reaction. So the forward reaction is very high. That means that because there's no products, there's nothing but in this beaker of a solution, let's say, there's nothing but reactants. So they can only interact with each other. So they're interacting, they're mingling, and it's producing a lot of product very quickly because there's nothing interfering with these collisions of these molecules. So it starts out very high, but it starts decreasing, and it's decreasing at the same time simultaneously that now product is being formed. So the rate of product is also forming, but with that rate of product means that it's also now starting to push back into the reactant side. So this is starting to increase while this side is starting to decrease because more products being produced, until eventually they are at the same rate. And this line here, this point, is the equilibrium, so the double arrows. So as one starts high and then starts decreasing, because there's not as much reactants because it's being produced into product. And then now with the product being formed, it's starting to increase a reverse reaction where there was not one when it originally started. So the horizontal line represents the equilibrium being reached, and equilibrium is the double arrows. So when I discussed concentration earlier, I said they don't have to be equal, and they're not going to be equal. It's just when the equilibrium is locked in place. Whatever those concentrations are for the reactant and product side, they're going to stay the same when equilibrium's reached. So if we look here on the y-axis, this is molarity, moles over liter, and this is the progress of the reaction. So a plot representing a decrease in the concentration of reactant, which we expect because as the reactants go to product, there's going to be less and less of it. So a plot representing a decrease in the concentration of reactant falls and then eventually levels out. And that's because it hits equilibrium where there's no more being pushed more than what the reverse rate is. They will become equal. And then a plot representing an increase, so if we're here at the blue line, an increase in the concentration of product rises from the origin because it starts at 0. And then eventually rises above the origin of the plot for reactants, because now there is amount of product that's been produced, and eventually also levels out. So the point where both these extend out horizontally, even though they're at different levels, this is the equilibrium. They have one increases in concentration because you start out with no product, so there is nothing there, and one decreases. So as one increases, the other one's going to start to decrease because you have to take away the amount that's being produced from you have to take away the amount from reactants to what's being produced in the products. So here is rate of forward reaction. So this also is very similar to this. It just breaks it down and to be more specific about what's happening. So if you notice here is our forward and reverse reaction. We have hydrogen and iodide, okay? And we have times, and these are all in hours. So H for chemistry is H. It's not HR, it is H. So this is 0 time, 1 hour time, 2 hour, 3 hour, and 8 hour. Concentration of reactants, concentration of products, rates of forward and reverse reactions. So you can see how big the arrows get tell you what is happening. So at time 0, we only have reactants because we don't have a product because the chemical reaction hasn't occurred. So they're letting you know that there are 8 molecules in here, 4 and 4. So that means that they have 4 hydrogen and 4 iodide in this. So equals 8. But what we expect to happen is as the product is produced, we're going to lose the concentration of reactants because some of that has to be taken out to show that it's been produced as a product. So when we look at 1 hour, we notice that the concentration has gone down. It's gone down to 6, which means 2 has gone over to be produced as product. So you can see we have 0, no blue arrow here. Now, as the products are being formed, they are starting to collide, just barely, and they are starting to push back into the reactants. So that's why you see a very small arrow. Now, as we get to 2 hours, we are down to 4. So we have 2 molecules of hydrogen, 2 molecules of iodide, and then we have 4 molecules of hydrogen here. And with the 2 hours, we can see that we have a medium length, let's call a medium length arrow that for the forward, and we have a slightly bigger reverse arrow. So now more is starting to be pushed back from the product into reactants. And then at 3 hours, we have 2 moles of reactants and 6 moles of product. 2 molecules of reactants, 6 molecules of product. And we have arrows that look equal to each other. And then as we jump to 8 hours, the circumstances have not changed. So it's not stated here is that at 3 hours, this reaction has hit equilibrium, and 8 hours, 5 hours later, it's still at equilibrium. And the system will not change unless something's done to the system. So the concentrations don't have to be equal, but once they are locked in at equilibrium, those concentrations are going to stay those concentrations unless something is done to the system. And in this case, it's 2 molecules of reactants and 6 molecules of product. So in the reaction, the forward reaction is given here. And you can see that was what was producing with hydrogen iodide. And the reverse reaction is just flipping this. So we have our product, but it goes back to being produced into reactants. So as the hydrogen iodide product builds up, the rate of reverse reaction increases because we're getting more product that will interact with each other, while the forward reaction decreases because we're losing the concentration of a reactant because it's going into product. So a reaction reaches equilibrium when no further changes take place in the concentration of the reactants and products. At equilibrium, the rate of the forward reaction is equal to the rate of the reverse. That's when you get the double arrows that look exactly alike in length and size. The forward and reverse reactions continue at the same rate and will continue until something disrupts that system. It will stay that way. So here is another way to look at this. If we start with reactants of SO2 and oxygen, the reaction will form SO3 and takes place into equilibrium is reached. So that means eventually some of this will be pushed back in here. But what they want you to look at is here. So they want you to forget this middle part. They want you to look at initially the original reaction. So it's with sulfur dioxide and oxygen. It doesn't have a product, but as it starts going, it'll eventually push itself into the product, which is C. So we're not looking at the equilibrium, we're looking at C. So it eventually will push itself to C, right? Now, forget what I just said and only look at as sulfur trioxide as if this was the reactant. What it'll eventually do, if there's a reaction, it will eventually push itself back into, because these will collide with each other and push themselves back into sulfur dioxide and oxygen, which eventually, no matter which way you start with, it will come to an equilibrium reaction that's in the middle. So even if you start with the SO3, C, you're going to get to B. And if you start with A, you're going to eventually end up with B too. So either way you come at this, you're going to end up with an equilibrium of, and there's the double arrows, and whatever the concentration amounts of both of these are, that's what's going to end up happening. So let's do a little bit of testing on this. Complete each of the following with is or are equal, or is or are not equal, changes, or does not change. Before equilibrium, so now this is before equilibrium, so it's telling you that this is not equal. is reached, the concentration of the reactants and the products. So I'm not going to pick is not equal because it's pretty obvious by the fact that it's saying it's before equilibrium. But what I am going to pick is change. So before equilibrium is reached, the concentration of the reactants and the products change because they will not change once everything hits equilibrium. At equilibrium, the rate of the forward reaction blank to the rate of the reverse reaction. This is equal or are equal to. And that's it right there. So let's go on to the next one. So let's take a look at this here. So complete each sentence with whatever these words are, and as we read the bottom. So A, reactants form products in the blank reaction. At equilibrium, the reactant concentration blank, and products form reactants in the blank. So reactants form products. When do reactants form products? In the forward reaction. And now let's just jump to C. Products form reactants in the reverse reaction. And at equilibrium, the reactant concentration should not change because once we get into equilibrium, those concentrations lock in. And there you go. And that's it.